Okay, now, part of the reason for these kind of changes in the rate at which oxygen is taken up based on a change in partial pressure. So we're talking about kind of this portion of the curve and that portion of the curve here, as well as a little bit into here and here. And that is the hemoglobin molecule is kind of unusual in that the ease with which oxygen attaches or lets go of hemoglobin depends on how many other oxygen atoms have already bound. So let me just go back to this situation where none of these iron atoms currently have a have an oxygen attached to them. I add an oxygen here. This increases the likelihood that oxygen attaches to the other binding sites. Right? Getting one to attach is hard, but once you get one of them to attach, it's easier to attach the second one. Okay? And the reverse situation is also true. It's hard to get hemoglobin to let go of an oxygen, but once it lets go of one, you increase the likelihood of letting go of others. That's shown in this part of the curve. Okay. All right. Now, let me redraw this oxygen hemoglobin dissociation curve, because I want to talk about an important part of this. This is still partial pressure of oxygen in millimeters of mercury, and this is still percent saturation of hemoglobin with O2. Okay? And then we have this kind of weird looking curve, which was the oxygen hemoglobin dissociation curve. Oxygen hemoglobin dissociation curve. Now, the binding of hemoglobin to oxygen, it's sensitive to how many other oxygens have already bound. Right? I said once you attach one, it's easier to attach more. That gets us into this steep increase in saturation. But the ability of oxygen to bind is also affected by the pH that the hemoglobin finds itself in. Okay? So let's walk back through that dynamic equilibrium that I set up a while ago, I guess a couple weeks ago. I said that CO2 in the presence of water, some of this CO2 will become soluble and make that's that carbonic acid, and then the carbonic acid would dissociate into this. That's bicarbonate. And I said we could continue this if we were in a lake, but in us, it pretty much stops at this point. And this I called carbonic acid. Okay? Just taking a look at the time here. All right, so my expectation is anywhere in the body where there's high metabolic demand. So let's say I'm sitting here doing nothing, right? But I'm twiddling my thumbs. Now, my thumbs, lots of muscles being activated, right? Lots of ATP required to get these muscles to work. So in that particular portion of my body, where my thumbs are, I'm doing lots more cellular respiration in order to make more ATP to do more muscle contraction. Wherever ATP is being manufactured, there are two things that I expect to be happening. The first is the concentration of oxygen should be decreasing because the oxygen is being, right, the oxygen is being consumed locally, right? And I expect an increase in CO2. So if CO2 increases locally, what is happening to the dynamic equilibrium? Well, dynamic equilibrium with an increase in CO2 results in the production of more carbonic acid. And as more carbonic acid is produced, what happens to the dynamic equilibrium? It pushes again to the right, and it leads to this. An increase in the concentration of hydrogen ions. An increase in the concentration of hydrogen ions results in a decrease in the pH, because it's a backward scale. Increases in hydrogen ion concentration, decreases in pH. Now, the decrease in pH has an effect on hemoglobin. Hemoglobin's ability to bind oxygen is affected directly by the pH. The pH change affects this oxygen hemoglobin dissociation curve. So at a typical pH here, right, let's call this typical pH right here, 7.4, right, pH of 7.4, and now locally in this tissue, I have now a pH of 7. The pH has dropped because I produced more CO2 in that area. The pH is dropping. That's going to change the shape of the curve. Now I've over accentuated it, right? So you can see it on the video, but here the Bohr shift is describing the change in the oxygen hemoglobin dissociation curve with changes in pH caused by changes in CO2 concentration. Okay? All right, so what we're going to do for next time is tear into the Bohr shift, and then I think we're headed to the digestive system in all of its glory. So I hope to see you next time. Bye.